I want to determine the relationship between plane P. P, right, is R dot 1, negative 2, 3 equals to 2 and each of the following line. So you must remember last time you solve everything in terms of Cartesian, x, y, z, x, y, z. Now it's the same. You try to make x, y, z the subject and then you sub into, use x, y, z as the common thing to sub. So for first A, right, you have L1 x minus 2 over 2 equals to y minus 1, z equals to 1. You try to form a vector equation of the line. Okay, so from here, right, you can quickly form, you just, I'm sure you can do by yourself. Okay, so you R equals to 211 plus mu 210 and your mu is a real number. Lambda is 1. Okay, right, so from here, I need to check the relationship between this and this. How do I go from here to here? How do I go from here to here?
First line.
Oh no, the first two lines, they are different. What? This one is a plane. This one is a plane, right? This one is a line. This one is a line. This one is a vector equation of a line. This one is a vector equation of a plane in scalar product form. There are three forms of vector equation for a plane. There's one is the parametric form, scalar product form, and the Cartesian form. Okay, so for this, right, how do we check the relationship between them? Number one, first one we try to check parallel. Parallel is the easiest to check. Also, how to check parallel? You agree with me? Let's say I give you this plane, right? This plane will have a normal, right? You have a normal, correct? So you know, just now we have the equation of the plane to be like this, right? It was originally in this form, right? So my question to you is, what is this? What is this vector? Is the okay, this one, right? What does this mean? What does this represent? This particular vector, what does it represent? It is the normal vector to the plane. Don't know. Okay, quick, go back. Now we go back to question. Then we must go back again. Okay, go back to. We go back. Okay, I quickly say again. Okay, vector equation of plane got how many types? How many types? Got 3 types. Okay, first one is what? Vector equation in parametric form. Okay, parametric form for the plane. So it's like this. Okay, last time if I want to describe a line, I must, you see how to describe a line is based, I must grab one part of the line, right? Have a position vector first, then I say, oh, this direction. Grab a point, I say this direction, that's the line. Now, how do I describe a plane? I grab a point on the plane, then I have one line here, I can describe any point on the plane. Because you can see parallelogram law of addition. If I have one point, I have a plane, I put a point on the plane, I put one vector out, I put another vector out, must be non-parallel, right? I can describe any point on the plane, right? Any point on the plane. Okay, because like parallelogram law, right? Remember parallelogram law, if I take A, B, then this one is B. This vector is like A plus B. 记得吗, Ethan? So from here, right? So that's why to describe a vector equation in parametric form, we need one position vector of the plane. One is A. We need another direction vector on the plane. Maybe it's called M1. A plus lambda M1. And a scalar multiple of M2, where lambda and mu are real numbers. Okay, one position vector on the plane, M1 and M2, can sweep throughout the whole plane to give you the direction vector, position of any position vector on the plane. Okay. If cannot, you have to swallow. You must memorize. You have to memorize. Monisha, okay.
Draw same, but I don't know how to read it.
This one no, just like going back. Ether, okay. Correct. But you must know why it works like that. Next one is what? In scalar product form. R dot n equals to D. Right? Another way to describe a plane is I can use the normal vector to describe the plane. So what does this mean? This one it refers to what? Ethan. Refers to what? So we can say it's normal vector. Normal vector, okay, this normal vector to the plane. So after that, what is this? This one is just A dot n, where A, this is the position vector. This is the position vector of a point on the plane. This is the normal vector or perpendicular vector to the plane. Okay, you need to remember this. Why is it I went back to go through this? Because just now when you all saw examples question 7, you all don't understand what it means. So now I go back to tell you. A vector. No, cannot. Doesn't mean that. The figure, okay. So this one is just okay. So R dot n, R is your x, y, z. Okay, so this one, right, you A dot n, right? A is a point on the plane. This one is your plane, right? This one is your n. This one is your n. Okay? A is a particular point or position on your plane. Sorry? Okay, anywhere. Okay, maybe you can put somewhere else. Put somewhere here. You can put somewhere here. This is A. Okay? R dot n is any x, y, z on the plane. This is any x, y, z on the plane. Okay? So this is the vector equation in scalar product form. Why is it this way? Go and read the comprehensive notes. It will tell you how we deduce a vector equation in scalar product form. Okay, so this part, do go and read the comprehensive notes. Got question or not? Don't have.
So R can be any vector.
R is like when I give you a line, right? When I give you a line, y equals to 2x plus 5. I can describe any point on the line. Any point on the line can be like x, maybe x, y, something like that, correct? But you must follow the behavior. If this side I have x, the other one must be 2x plus 5. Why must be 2x plus 5? So it's like a behavior that guides the whole line. Okay? Similarly, R, okay, this is my plane. R is, is like your x, y, z. This is any position vector on the plane. Any position vector on the plane, dot product with n, alright, is equals to A dot n, where A is lying anywhere on the plane also. A is passing through a point, okay, so it's passing through a point A with position vector A. So again is you can say somewhere here. A, okay, lies on the plane. So it is it looks something like that, okay, see, like umbrella like that. This is your A, okay, origin like that. This is the A. So the point A could be is the point A lies on the plane. The position vector A also directs it lies on the plane. Okay, this one is your A. So this could be the, maybe if your A is A1, A2, A3, right? Then this point A1, A2, A3 lies on the plane. It's a position vector. Okay, so with that, right, A, what we can do is every time to do the vector equation of a plane, we just grab one position vector on the plane. Okay, we grab one normal vector. So, yeah. Huh?
How do you draw R?
R is just any point. R is just any coordinate on the line, on the plane.
And will it link to the whole one?
Which one?
Or the R will it be like link to the whole also?
Yes, R will link to the whole. Everything will link back to the whole. Let's say I want to find this point, x, y, z. this is a generic point of the plane, right? You will always link back to the O. Because it's a position vector. All position vector will link back to the O. Okay? You take the whole thing. You check. Question 7. This is question 7. Question 7. Huh? You don't want? Oh, okay. I thought you would take. Okay. Okay. So with that, right, we go to question 7, right? Question 7. Okay, question 7. Okay, you see. First one, right? The plane R. Okay. R dot 1 negative 2 3 equals to 2. Okay. Then the line L1 x minus 2 over 2 equals to y minus 1 equal. Okay. Then comma z equals to 1. Okay. From here, right? This is a what kind? In what form of the line? What kind of equation? Line or plane? This one. Line, right? Cartesian or vector? Ethan? Cartesian or vector? This one? Cartesian. Why Cartesian? Because it's in terms of x, y, z. Can you see? This one is in terms of x, y, z. X, y, z is Cartesian. X, y is Cartesian. Okay. From here, right, we form the vector equation. It just equals to 211 plus mu 210. 210. Mu is a real number. Okay. So this is the direction vector of the line. Okay. Can you tell me now what is this in reference to the plane? What is this? The normal to the plane. Very quickly, first thing we do is we check. When we want to check relationship between line and plane, right? One thing we can do, we check whether they are parallel. That's the one thing. How to check that parallel? I give you a plane, right? This plane, the normal is like that. Okay, there's a line. What if I can show that the direction vector of the line, if the normal of the plane, right, dot product with the direction vector of the line is equal to 0, what does it mean? It means that the line is line perpendicular. Why parallel? If I'm perpendicular to your normal vector, it means I'm parallel to the plane, right? Can you see? 你真可以吗？lost it. This one is the plane, right? This one is the normal, right? Now I got one line. My direction of the line, right? Dot product with the normal vector is 0. That means I'm perpendicular to the plane. I'm parallel to the plane.
If your line is like that and your plane is this stable, this is also considered parallel.
Yeah. Okay. All parallel. All parallel. Okay. You see, this is my. This one is my normal vector, right? My line can be facing here. My line can be facing there. Doesn't matter. As long as my line, right, dot product with this like normal, right, is 0, right? This says something. That means my line is hanging this way. It's parallel to the plane.
What do you get the simple one? The R
R
equals to 211 plus.
equals to 211. This is the equation of the line. The question is like that. You have the question paper, right? L1 is x minus 2 over 2. This is y minus 1. This is z equals to 1. This is the vector. This is the Cartesian equation of a line. Okay, in terms of x, y, z. I want to make this a vector equation, right? So very quickly, I make lambda the subject. Lambda is x minus 2 over 2. Lambda is equals to y minus 1. Lambda here, just z equals to 1, nothing. Okay? So here, 2 lambda plus 2 equals to x. Lambda plus 1 equals to y. Okay? Here, nothing about lambda. Then from here, can you see if I make x, y, z the subject? X equals to 2 plus 2 lambda. Y equals to 1 plus lambda. Z equals to 1. Nothing, actually just 1, I rearrange this. This is 211 plus lambda 210. 210. So this one is vector equation. Okay? Then very quickly you can see this is the direction vector of the line. Okay, so direction vector of L2, right? Of L1, sorry, is actually 210. Normal vector of P, right, is actually equals to 1, negative 2, 3. So the direction vector of L1, right, is 210, right? Then the normal vector of P is 1, negative 2, 3, right? And then, these two dot product is 0, right? That means if my direction vector, right, is perpendicular to your normal vector, right, that means I'm parallel to your plane. My direction vector, right, is perpendicular to your normal vector, right? That means I'm parallel to the plane. So I realize, this one actually gives you 0. Do you get 0? How can I get 0? Quite easy, yeah. 2, 1, 2. 1, negative 2, 2. So it's just 0. So from here, right, we can say L1 is parallel to P. Is that okay? That's for part 1 now. Okay, after that, next one. That next thing is if parallel, it can be that it lies on the plane, or it could be that it's on top. It's on top. Okay, so now that it's parallel, it could be this scenario. It could be lying down like that. It could be lying down on top or below. How do we know which one? We take a position vector and try.
Now you're trying parallel on the plane or it's floating?
Yeah, it's floating. Whether it's on the plane or it's floating.
How do you determine dot product?
How do I determine the dot product again? Which one?
How do you know dot product?
How do I determine? How do I do this one?
Like because you don't. Right now you don't know what is the relationship in the first place, right? So how do you determine to do that?
Okay, so always, right, I always try to check the easiest step. The easiest step is try to see whether they are parallel. How to see parallel? Very easy, just dot product. Dot product very easy to do, right? Some questions they will tell you, intersect already, go and solve now. So then you can solve. Sometimes you must know, they will tell you it's parallel. So we check. Usually we check parallel first. To check relationship between two lines, right, whether they are parallel, right, you just check the direction vector, whether they are scalar multiple. But I want to check between relationship between line and the plane. You use the direction and the normal vector to check. The relationship between a line and plane got a few types. So one of the ways in which it can be like this, is intersect, hit. This kind we can find for intersection. Number 2, it can be a plane this way, and the line is lying on me. This is the plane. Let's say the table is my plane, I lie down. This one is the line. So it just sits nicely inside. Number 3, right, it can be here, and my line is floating on top. This is my plane, and my line is floating on top. Can, right?
Yeah.
So the only way for it to be floating, right, it has to be parallel. Okay? Because let's say it's not parallel, it's like that, right? A line has no start and point, right? So that means it will go on and on until you touch the plane. So this kind of relationship, right? One way is you can see, if I use the normal vector of the plane, and I the direction vector of the line, right? Then you see actually if these two, right, let's say A and B, right? Let's say A dot with B equals to 0, right? That means this line is parallel to this, right?
Yeah.
The line is parallel to the plane. That's how I see it.
No, if A dot B equals 0, then you're saying this and this is perpendicular.
That means B if I'm me and you are here. Let's say we face each other. This one right, line point towards you. If I dot product with this is 0, right? You dot product with this is 0, right?
Yeah.
That means we are parallel.
Oh,
Can I say because this one right by default right, is a normal vector to the plane. That means one is confirmed is perpendicular to the plane. Oh. Okay,
so this was taught to us like in practice 1 that A dot B equals to 0 if the B and the plane is parallel.
In vectors 1 they didn't teach plane, they just taught like in general right, two vectors right. With two vectors A and B right, A and B are perpendicular. Okay? If and only if A dot B is equals to 0. So why is it? Because you can see that A dot B right, by definition right, A dot B right, this will be mod A, mod B, cosine theta, where theta is the angle right between A and B. Then let's say right, if they are perpendicular right, that means this one is 90 degree right. That means this one will be 90 degree. So this one will be cosine 90. Cosine 90 is equals to what? It's just equals to cosine 90. Cosine 90 is just equals to 0. So therefore this one equals to 0.
Okay, yeah. So I get all that. I get all that until here. So I'm saying that once you get these two vectors right, my question is like, how do you form that thinking that using A dot B equals to 0 will give you that the plane and your vector B is parallel?
So it's like what I told you just now. So I want to have a line. This line right, I have I don't know what it looks like. I don't know what it's like. Okay, so how do I form it? First thing, that's why the objective of the question right, is to tell you, actually when you want to find a relationship right, one of the way, the first way right, this lecture got said before, you could check parallel.
So I always check parallel first.
Correct.
But then if that's the case, then why don't I just go straight to like doing something? Well, I just find the vector equation of a plane then instead.
Vector equation of plane got 3 types, right?
Yeah.
So here actually 我已经给你那个 vector equation of plane 了。So I gave you this in this form. So why do you give me in this form? 1 negative 2 3. Oh, that means you are telling me that the normal vector to this plane, n right, is 1 negative 2 3. This is my line. My line right, in this form I cannot do much. But I know that actually if I write in a vector form, because they will assume that actually you are very proficient in it, you can switch from Cartesian to vector form. So they assume you can switch 2 1 1 plus lambda 2 1 0. This is your line, this is your plane. How to see a relationship? One way is you can compare the direction vector. My normal, if this and this dot product is 0, then the line and the plane are parallel. So how to form this thinking? Really, it's like you do one time, then you know. First thing you do is you must check the parallel.
So
there's no math. There's no like one size fits all or one algorithm fits all questions.
okay.
So I think they will tell you, you try to check the relationship between the line and the plane.
So I check it first whether or not it's parallel.
Correct.
So after this, so I say that because it's 0, therefore it is parallel. Therefore it is, because it is 0, these two are perpendicular. So therefore the plane and your vector B is parallel.
Correct. So the question looks like that. Okay. So see, this question 7. So it looks like that. It does not. So since you go 0, it is parallel. That's all. Can you see? Actually, it's very trivial.
It's false. But it does equals to 0 after that.
If I give you A equals to 1, 2, 3, I give you B equals to 1, 7, 5, right? A dot B is what? A dot B will just be equals to 1, 2, 3 dot with 1, 7, 5. Then it's just 1 times 1 plus 2 times 7 plus 3 times 5. So it's 1 plus 2 times 7, 14 plus 3 times 5, 15. Answer come out 30. So you see it's a number, not a vector. So here actually is not yours as well. Then A will be perpendicular. So this one actually why is it not true leh? Because right, A right can be a zero vector. Very simple. What if A is just 0, 0, 0? Right. Then of course if I dot product any vector is 0, 0, of course it's 0 lor. Then if I put B as any number, maybe 758, 758 like A dot B, of course goes 0 lor. But does it mean these two are perpendicular? No one. Because origin is like this one is 0, 0, 0, then 75 is somewhere here. May not be equals. It doesn't mean they're perpendicular. So if it's 0, 0, 0, A is a zero vector, then it makes no sense lah. So it's like here right, one thing A dot B equals to 0 imply A and perpendicular to B, right? This one is not true, false. But if A is perpendicular to B,
then it will be 0.
then A dot B equals to 0. This one true. Because of the angle between them.
Then A cross B is just the product period.
A cross B, right? So A cross B is like that. If this one is A, this one is B, right? A cross B. This is A cross B. It's a vector. A cross B is a vector. A cross B is a vector.
So when do we determine when to? Because there are some questions, right, where they have times. They have times, and then they can suddenly use A cross B or A dot B.
When you look at the keywords, certain keywords they ask for so the keywords are all here. So actually there are only four. This one, right? Okay, so when the length of projection, we heard the word length, that means you are giving a number of vector. You're giving a length. Length is it a vector?
No,
it's a number, right? So over here, right, the length of projection of A onto B, this one has A dot B hat. The one lying down provides the unit vector. This one is A cross B hat.
So this one must remember.
You can remember, actually the proof is in the comprehensive notes now. If not, actually I tell you.
Okay.
Fucking memorize. For I know, right, if you ask me to go and deduce a proof, I'll also take a while. I just memorize. I don't care. But this one is very easy. A, like that, right? This one, right? Okay, this one is A. This one is theta. I don't remember wrong. This one is, I don't know what is this now. That's why I call this the adjacent. Maybe the adjacent. Or I call this X now. Then you see first one is cos theta, right? Cosine theta is adjacent over hypotenuse, right? Right?
Yeah.
Cosine theta can also be written as what? So let's say if cosine theta can also be what? A dot. This one is B, right? B, right?
Yeah.
So it can also be A dot B over mod A mod B, right?
Yeah.
That's from the earlier part.
Yeah.
So it's equals to X over. So it's like if it's a vector, right? A, right? This will be mod A, right? This triangle, this length.
Yeah.
It's like X over mod A, right?
So when you mod something, it becomes like you square it.
It's like when you mod something, it's like
So you root it, then you add the 3 points to it.
this is the vector, right? So if I to find mod A, right, this would be square root. Let's say A is equals to like 3 components: A1, A2, A3.
So then A square plus A2 square plus
A1 square plus A2 square plus A3 square. Then the unit vector A hat, right? This is just A over its own magnitude, which is
I get it.
Okay, next one. Then so this portion you can see cancel off. Right? What is this portion? This one is just B hat. So next time you can see X is just equals to A dot B hat. This one is A dot B hat. Okay, so I think so very easy. You just really have to force it, memorize it.
Then for this one, like vector component of A as in like, so this one is asking for the length, right? And then this one is asking. So this is when they ask for vector component, they're asking for direction vector, is it?
Correct, they're asking for direction vector. This one, right, I mean, if you look at the triangle this way, right? One way we can see this line can mean a vector, this line can mean a length. If I draw a like this, right? For example, let's say I talk about this line. I draw a vector here. Okay, if this is a vector, right? This vector, okay, let's say I use blue color. Here I use green color. Here I use yellow color. Okay, you see. Okay, the vector, right? The blue vector, right? The blue vector, right? This one is equals to A dot B hat. B hat. But the length, okay, of the blue vector, right? This one actually is just equals to mod A dot B hat. You know why? So actually, if the length of blue vector is like I just mod this, right? If I say the length, if this is the blue vector, right? And if I want to find the length, it's like I want to find the length of this, right? I just need to mod it, right?
Yeah.
If I mod it, I can say I can speed up, right? So I just speed up. What is the length of this?
1.
Yes, 1. So 不用放咯。That's why you say this answer. Come on. Like that. That's why the answer is like that. Then the vector itself is A dot B hat dot B hat.
So technically after I find this, right, let's say for example like 2, 2, 2 like that, I can technically also find a length using this 2, 2, 2, right?
Correct. Very good. Then the green portion, sorry, I blank a bit since we are already on this. Then the green portion, green portion is just
so A minus B, like
correct. Let's say if this is A, right? The yellow portion will be A, right? So it's just this minus this, right? So we can say it's just green portion is just A minus A dot B. Alright. Or so this is this one is a vector, right? This one is a vector, right? The green vector, right? But we want to talk about let's say we want to talk about the length of the green vector. Length, right? We can say is A times B hat. Green vector. Okay. You can just memorize this. You can see I put 2 together so you can see very nice. One is vector, this one is length, this one is length. You can see both. This one will give you a vector, this one will give you a number.
So then vectors 2 also. This is so I just clarify from the last time so this is the line L, right? And this is the vector equation of line L.
Correct. Vector equation of line L.
Okay. Vector equation being not the direction vector, right? Not the direction vector.
No, direct vector. The vector equation itself, this one is a line, right?
Okay, but what does a vector equation mean?
Vector equation, you have vectors in the equation. So the vector equation of a line, because here, right, when we want to represent a line in space, we need a position vector. We need to grab one point on the line first. Because I don't need to grab one point first. Here, right, is reference to an origin.
Yeah.
This is the A. After that, this A, I want to show how do I represent something on this line.
Oh, okay. So the vector equation is there for you to help you derive the line
to start off the line. Then the M, right, is the direction vector. This M can indicate let's say I'll put one time of M, right? Then this position vector here, right? You can see this position vector here is like A plus 1M. 1M, right?
I get this.
So you can see, actually if I can manipulate this now, so it can become a lambda. So I can represent any point on this line using A, using M.
Then so line L can be represented. Is it the same as the direction vector?
No, direction vector is M. Why is it? Because two lines, right, can have the same direction vector, but doesn't mean they're the same line.
So this line L is like infinite
Correct.
And then so therefore like this line, so the vector of the line will be the vector equation of this line will be like M like that and this vector the direction vector of this line is this M here, which will be parallel to to the line L.
Correct.
But then the vector equation is used to deduce the vector equation is used to deduce the direction vector using this like
The vector equation of a line is like everybody has a name. This line, the name of this line must be its own vector equation. To describe a line, we need to let's say for example, I want to describe you. I say, okay, handsome boy, Chinese, 2 things. I want to describe this line, I need 2 things. I need a position vector, I need a direction vector.
Yeah.
Okay? Why? Because it's just like I say handsome boy, but can be a lot of handsome boy. I want to say Chinese, can a lot of Chinese boys. I want to say direction vector is 1, 2, 3. This could be 1, 0, 2. This vector here could be 2, 4, 6. Could be both of them have the same direction vector. Maybe this is 1, 2, 3. This also got 1, 2, 3. Both have same direction vector, but not the same line.
Oh, okay.
That's why we need both things. One is position, one is direction to describe this line.
So this one I find very weird. So over here they say this equals to lambda, this equals to lambda, this equals to lambda.
Correct.
So in this case, like where we did just now,
Z equals to 1, that one.
Yeah, z equals to 1.
Very good. Okay.
So what they're saying over
just means that lambda is not represented, and then lambda is equals to 0.
So this Cartesian equations, like you were saying, like it's like the points on the thing, so like 1, 2 like that. But then when they ask for the Cartesian equation, do I show it like this?
Yes, you show it like this. X minus something over equals to y minus something over equals to z minus something over.
But if like the z is already, so if it's not unknown.
If it's not unknown,
then I can just write z equals to whatever.
Correct. So example, like just now that one, it was something like maybe x minus 2 over 3 equals to y minus 1 over 2. Have that comma. Z has no lambda, so z equals to 1. This just means that so like lambda equals to x minus 2. So because everything here, right, where you see lambda disappear because mainly of lambda is the subject, is x minus 2 over 3. Lambda is y minus 1 over 2. Here, 都没有 lambda, nothing, right? It's not equal, right? So this just means that z is 1. It's just 1. It's just 1 without any. So here, right, 3 lambda I shift over plus 2 equals to x. I quickly do the manipulation. Here, 2 lambda plus 1 equals to y. Z equals to 1. So x, right? Y, z is like our r, right? Our r is like this, right? So x is equals to what? Equals to 2 plus 3 lambda. Y is equals to 1 plus 2 lambda. Z is equals to just 1 plus 0 lambda. Let's say that's why. So from here you can write out the vector equation 2, 1, 1 lambda 3, 2, 0. Remember, right? Lambda is a real number.
Okay. Then I have for this one. Okay, so this is the vector equation of plane P. So plane being like this, right?
Correct.
So like if this is a plane, I have I got A, which is like some
point here. Some point here.
Then plus
reference to an origin. Okay. Okay.
So then they say lambda m plus mu m. So it's like there's one more and plus one more. Is it?
So example, it could be something like this. I have this plane. I have one position vector on the plane. This point could be 1, 2, 3. 1, 2, 3. And this means that it's reference to its origin. This is the vector 1, 2, 3. Alright. Then I want to describe a point on this plane. Maybe let's say I have a vector here. This is 1, 1, 1, 1. Okay. This one could be 2, 3, 4. Something like that. 2 non-parallel vectors. Okay. So from here, right, the position vector. What's the position again? So this one is your A. This one is the A. This one is the M1. This one is the M2. 就是这样，基本上就是这样。
So then you have lambda and mu. So it's like connecting one here like that.
Lambda and mu are scalar. Lambda is scalar. So let's say I look at this, right? Let's say I want to check if I have a point on the plane. This point is 4, 6, 8. Okay, let's say this point is 468. Okay, can this point be represented by this? Can this point is on the plane? Can you realize that actually 468 because the equation of the plane is like that, right? This is my equation of plane. 1, 2, 3 plus lambda of 1, 1, 1 plus mu of 2, 3, 4, right? This is my M1, M2, right? Because again we go back to our equation. A plus lambda M1 plus mu of M2, right? Then say 这个可以吗can lambda equals to 1 mu equals to 1 1 plus 1 plus 2 4 2 plus 1 plus 3 6 3 plus 1 plus 4 8. So when lambda equals to 1 mu equals to 1, right, you can see that 468, right, satisfy this equation. So it's the P. So basically what I'm telling you is like any point on the plane, right, can be represented by this. Can be represented by this. Yeah. Slowly.
Very hard to visualize.
Very hard to visualize. It's freaking hard, I tell you. But it's just like I give you this A, right? I give you this B. It's freaking hard to realize. So this A, what I'm trying to sell you, right? This one is your starting point.
Yeah.
But A and B can represent any point on the plane. I put maybe a point here. This point can be represented by something A, lambda A plus mu 1B, something like that. Because parallelogram law addition. So if lambda A, so maybe here lambda A will look something like that. So it's lambda A. Maybe lambda A. Mu B, maybe mu B somewhere here, shorter. Mu B. Correct? And parallelogram law addition is not 1, like that, 1, 2, maybe something like this. Parallelogram law. This one is lambda A. This one is mu B.
So then this is the plane that we're talking about.
This plane we're talking about. I'll give you another vector, another stupid vector. I say like another lambda, and then this is A. This one is B. Again, I want to point some vector here. I say, hey, now play I want this point here. Can this point be represented by A and B? Can. I draw a line here.
So can you go back to the previous page? Lambda. So this being M and M1 and M2.
This one will be the M1.
So what's the A again?
A is a fixed point. This one is your A. This one is like a starting point.
Okay.
A fixed point on the plane. So here the same A and I say this one can it be represented? Can. Maybe I increase. This one I increase some more. This one is my maybe 2 times of B. This one maybe 1.5 times of A. Parallelogram law. Can, right? So this one also can represent. So basically any point, I give you 2 vectors, you can represent any point on this plane.
Then this one, what is D?
D is just it's also a bit hard actually. So D is just a fixed point. So it's just a fixed value. It's represented by A dot M. A is a fixed point on the plane. A is a position vector on the plane. So for example, this one like that. Okay, so this vector here is A. This one is your A. So A could be a point on the plane, like 1, 2, 3, point on the plane. N will be a normal to the plane. N, you can find a normal to the plane. So what does it mean? You know, at the N, right? They say how to find this N sometimes, right? Got a lot of situation. I want to ask you to find equation of the plane. I got situation. Maybe I can give you one vector that lie on the plane, M1. I give you, let's say I give you this way, M2. Okay? I give you a fixed position vector A. Is it OA? Like that, right? Can you find equation of the plane? Can, right? Because you got just put A plus lambda M1 plus lambda M2. Okay? So this one is the vector equation in what form? What form do we call this? This is the parametric form. Okay, parametric form. Okay? Very good. Let's say I want to find now R dot N equals to D. How do I find it in scalar product form? It means now we need to find the N, right? We need to find a D, right? Okay, so how to find the N and the D?
So N is the perpendicular to
So now, again, you have this, right? We need to find the N, right? We need to find this N. How to find this N?
grab a point on the plane and then.
So vector product A and B, right? A and B, right? It will give you this A. This is a vector product A, B. It will give you a
so
vector
you
that
have
is
two vectors down here, and then it will provide you the.
very good. Yes. Now you are thinking. Okay, so we see. That's precisely what they do here. Okay. That's the idea of the question. 1, 2, 3 parallel to this and this, right? Find the equation of the plane. So one example. Now got 1, 1, negative 1, 1. This one is 2, 1, 2. Correct? Example, another line. How to find this n? Take these two cross product. So I take these two cross product, I get my normal vector. Yeah. Position vector can 1, 2, negative 1, 2, 3 lies on the plane.
So then this point is below n.
This point will just be any, may not be below n. Any point on the plane. This is just a point on the plane. A point on the plane. R dot n, right? R dot n, right? Equals to D, right? N will be a normal vector, right? Normal vector. And R is just any x, y, z. And D will be A dot n, where A is a fixed point on the plane, a fixed position vector, point A with position vector A on the plane, N is a normal vector. So in this case, how do we go about doing it? Let's say I use this as an example. I use question 5A as an example, right? I have one plane, right? So it's very good to draw. I have one point, 1, 2, 3. I have one vector, that direction vector lies on the plane. It's 1, negative 1, 1. I have another vector that lies on the plane, 2, 1, 2. Okay? Very quickly, I want to find this normal vector. I want to find a normal vector, right? And I take 1, negative 1, 1, cross product, 2, 1, 2. I get my answer. I get a negative 3, 0, 3.
So this is your n.
This is my n. Now, I have this A, right? This is so-called the fixed point, right? So A, quickly, I want to find my D, right? D is just A dot n, right? So it's just 1, 2, 3 dot product with negative 3, 0, 3. I get negative 3, 0, 9, negative 3 plus 0 plus 9. Answer come out 6.
So then this is like a constant.
A constant.
Constant that I can use to find the vector equation of the plane, which is R.
Correct. So here, right, based on this, right, R dot n equals to D, right? The D we found earlier is 6, so equals to 6. What is n? N is we found negative 3, 0, 3, right?
So the vector equation of plane P is not this, the vector equation of plane P is D over n, something like that. It's using the constant to
using a constant to so it's like I hear, right, R is any point on the plane, right? R dot product with its normal vector, I can give you that particular constant. It's fixed throughout.
So in this case, R dot n like this, right? If I end up with something like this equals 6, right?
Correct.
Then I stop like that.
Correct. That's the answer. Then you see R dot n equals to D, where D is equals to A dot n. A dot n we have found already. This already is the vector equation of the plane in scalar product form.
But I thought vector equation is like this one. It's R equals to something, and that something is your vector equation.
R equals to, okay, so you must remember now because you study more and more, I get very confused. Vector equation got line.
Yeah.
Line, right? Two things. Position vector, direction vector.
Yeah.
Vector equation of plane got 3 ways to describe. First one, vector equation of plane, right? Vector equation. So vector equation of plane. Okay, number 1 can be the parametric form. Parametric form, like I say, right, you have one start point, A, position vector, plus 2 hands, lambda of m1, plus mu of m2. Okay? Where lambda and mu are real numbers. That's first one. Second one, I can have it in scalar product form. Scalar product form, right, is just R dot product with n equals to D, where D equals to A dot n, and A is the position vector of a fixed point A on the plane. So total got 3, 1, 2. Third one, right, very easy. Third one you know how to do now. Third one is just like that. Let's say my n, right, I call it the normal vector, right, it has some vectors, right, component, right. For example, A1, ABC. Let's say just ABC. Let's say my normal vector is ABC. Okay, from here, right, R dot n equals to D, right. R is what? R is just your R, which represents the XYZ. Today. So I always say R is a short form for XYZ. R is a short form for XYZ. Okay? R is a short form for XYZ. So very quickly, ABC so means what? This is just like XYZ dot product with ABC, right? Equals to D. Dot product, right? AX, BY, CZ. AX plus BY plus CZ equals to D. This is the third form. You can see in terms of XYZ, right? What kind of form is this? This is called the Cartesian form. Very good. It's called the Cartesian form of the plane. Okay?
So this is the XYZ of the plane.
This is the this is how the XYZ are related. This is called the Cartesian equation.
Okay.
Yeah. So three ways vector plane got three ways to represent the equation. First two ways what scalar product and parametric can also be Cartesian equation. Okay. Line got Cartesian form, got vector form also.